Yep.
Because, you know, look, I feel like I don't really want to end up doing a lot of text. I mean, this is kind of the way it's going, and I'm not going to have to do it. And I hope that this is going to be very cool.
Good. Wonderful. There's also there's a lot of tech plugin for Google Docs that I used a lot over the last few semesters. It's a little wonky, but
The equation here,
it is cool. Basically, all of them uses
Well, neither of them work.
format, and you put format, and it just replaces the image.
You want to just speak?
Yeah. Hello, hello, hello.
There's a lag, so. No. I am more audible than you are. I don't know.
Turn this on.
I guess.
Sure. We can talk about that.
Let's remove it.
Yeah. Oh, removing it just cut out the audio, so it's probably this. Oh, but no.
It wouldn't.
Oh, yeah, yeah. Oh, yeah, I think it got.
Hello, 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 hello.
It's still being weird.
Do you think it's the mic on the, like, I don't know where it is on Mac, but do you want to restart OBS?
We can also plug in the
mic directly.
yeah, because I have two USBs, right? Yeah.
Let's try that.
Shouldn't have mattered, but
Wait, that's going to unplug what?
the mic and
Oh,
the clicker.
okay, that's fine. Yeah.
Yeah, we should just stop the stream. There's one here.
No.
No?
Yeah.
So
I can just stand next to the computer.
okay, let's do that, and I'll intervene if I can't hear you or something. I mean, you are still audible. It's just that I'm much more clearer than you are.
Yeah, that's fine. I'll hang
Keep
up.
both, just in case.
Okay.
Right. So I'll keep monitoring and I'll tell you. You can just do this.
And then blank.
Non-blank.
Gotcha. That'll figure it. So yeah, I'll do that in a second. Alrighty, guys, we're going to go ahead and get started. So today we're going to be talking about ways of visualizing neural networks. I'm going to talk about that for probably about an hour and 10 minutes, and then Ben, one of the other TAs, is going to come up and talk about using Docker, and just sort of we're all going to field questions about the homework if anybody's got them. Is that a question or?
Yeah, do we need our computers for to follow along with code on the first part?
So we're gonna pull up a Python notebook, but you don't have to worry about following along with it. It's not going to be super intense. It's just going to be demoing some simple things. So we're going to talk about just visualizing a simple hidden unit, then visualizing entire feed-forward networks, convolutional networks, recurrent networks, and then we're going to talk a little bit about attention. I know we haven't covered attention in class, but we're going to talk about at least just the general idea behind it, and then ways that you can use it to sort of visualize what's actually going on inside your model if you're using it. Then we're going to talk about ways you can look at visualizing high-dimensional data, and then just some sweeping generalizations about what visualizations can actually do for us at the current point. So hidden unit, this should all be review for you guys. Typically, it's it's squashing the input, some set of inputs between 0 and 1, or -1, +1, or if it's linear output, it doesn't matter. But let's say for this example, we're just squashing a set of inputs between -1 and 1. And then this is what we call a projection into the weight space. So hopefully this should all be review. So if we've got a set of inputs that it looks like this. So we've got a circle of blue points contained within a box of red points. This isn't linearly separable. So we can try and project it into some weight space. So this is a single layer. Or sorry, this is a perceptron. So we've got two inputs in, some x and y coordinate from this distribution, going into here, and then we're making some decision about whether or not to classify it as +1 or -1. And so the x-axis here is that decision boundary. So 0 in the center is the +1, -1 decision, and then the line is our projection. Anybody confused about this? We're just visualizing what a single neuron is doing. All right, so we can then try projecting it into 2 dimensions. So now we're projecting it not only onto the x and y, or onto the x-axis, but also onto the y-axis. So here, the projection is the same. The x-axis projection is exactly the same as the previous one, but now we've got an additional dimension added in on top of it, projecting along the y-axis. So we're still dealing with the same data. We're just kind of skewing it and then squashing it between -1 and +1, right? And then you can kind of do this ad nauseum. So this is up into 3 dimensions. We've got an x, a y, and a z-axis. Obviously, this kind of breaks down once you go into 4 dimensions. We're going to talk about ways you can handle that later. But this is kind of what you can think about when you're working with hidden layers. And if you want to try and visualize these things, you can easily trivially visualize hidden layers up to size 3 just by looking, graphing, plotting the outputs directly. Since you can plot them into a Cartesian space, you can do pretty much anything you want with them in terms of visualization. So this is just visualizing a simple hidden layer. We looked at doing it with one hidden neuron, 2, and then 3, and so you can just sort of do this. This only works obviously up to 3 examples, but we'll talk about it a little bit later. So clearly not linearly separable. We need to in order to separate this kind of data, we need to work in at least a 3-dimensional space. That way we can sort of skew the data in a way that, rather, we can project it onto a cone so that then we can slice the cone in half and get all the data on one point, or all the blue points on one side and all the red points on the other. And so to do that, let's talk about how we can visualize the actual outputs of the system. So here we've got a simple neural network, which is got 2 hidden layers and then finally an output layer. So we're projecting the data, the x and y coordinates, into 3 dimensions. Then we're projecting it back down into 2, and then finally into 1 dimension for the classification. So here, the cool thing about this is that this network is, all of the projections are within 3 dimensions, so you can visualize it pretty easily. And the other cool thing is that if you want to test out, if you want to determine your classification boundary for this kind of a network, you can just plug in some random x and y value and determine what the output is at that point, and then you can color a nice plot of your data and get the classification boundary. So that's what this looks like. So here we've got the red points are all on the outside and the blue points are all on the inside. And so this is the predicted this is the learned classification boundary. Then you're projecting it into 3 dimensions, and so you're kind of projecting it onto a cone. Yeah.
Question about the units plus and -1. This means that this is a binary network, or the max value is between 1.
So kind of these the visualizations, or the coordinates at least on on all of them actually, are all coming from the tanh activation. So because you're squashing these numbers between -1 and +1,
Yeah.
you're just you're plotting all these values along within that range.
But in reality, the unit in the network may not be in this bound.
So if you're using a tanh activation, then it will be.
Yeah.
But yeah, if you're using a linear activation or a ReLU or something like that, then it won't be. And so you're active. So if you do a plot like this, then it may scale differently.
Yeah. As I saw some paper talk about if the value is near the 0,
Mhm.
the neural network will be more likely in some nonlinear reality, right? Linear.
I don't want to make claims about that paper since I don't know, but that might be the case. I'd have to look at that paper. My intuition says that. Is it saying that if the values coming out of the activation are between are near 0?
Yeah, after the activate.
That would make some sense. That would make some sense, at least if you're using like a tanh activation, because then that's where the the slope of that activation function is steepest, is right around 0. So that would make some sense to me, but I don't want to make claims about that paper.
Yeah, it seems like the batch normalization technology is trying to do this. Right?
Mm-hmm. Yeah. So anyway, this is you're plotting the decision boundary of your classifier here. And again, since it's it's all within the different dimensions we can visualize, we get to get this pretty graph coming out of it. On the three-dimension projection, we're just plotting the sides of the decision we're just plotting the decision boundaries at the axes, as opposed to some volumetric craziness, just for the sake of visualization. So how many people just like this idea makes sense? Is anybody confused? Yeah. Any questions? All right, then we're going to move on. So the other cool thing you can do, and as opposed to writing my own visualization, I'm just going to use TensorBoard or the demo from TensorFlow, which actually lets you do some really cool things. So here it's showing that we've got 2 inputs, x1 and x2, and one is on the x-axis and the other is on the y-axis. And then it's actually showing you a sort of visualization of the linear separators that you're actually learning. So if we remove these and we do, let's say 3, we can run this and we can see that it'll eventually, hopefully, there you go, figure out some sort of classification boundary similar to the one that we were working with before. So you can see it's kind of projecting a triangle, as opposed, it's learning 3 different linear separators and then weighting them all together. So hopefully this kind of visualizes what each hidden layer is actually, or hidden neuron is actually doing. You can kind of do this ad nauseum, add a bunch of crazy hidden layers. Do whatever you want. This will overfit probably, but I mean, actually it's a simple distribution, so it probably won't. But a great distribution to see whether or not something is overfitting, or to see an example of something that's overfitting, is the spiral distribution. I think there was a talk about, one of the guest lectures came and talked about this distribution. But neural networks are really bad at learning this distribution. We are throwing a lot of stuff at it, so it might figure it out. But in general, things kind of fall apart with this one, and you get sort of weird islands of, islands for your classification boundary and things that don't work. Yeah, it just sucks. It'll get there, but it won't look pretty. And then yeah. So this is kind of cool, actually. A lot of times you'll see in your loss function plots this kind of jitter. And so that's kind of a visualization of what's happening. For some reason, it's very close to moving around a bunch of different bunch of the different classification boundaries, and that's kind of why your loss freaks out. You get spikes and stuff like that. But anyway, you can play around with this if you want. There are a bunch of other cool things you can do. So then let's talk about visualizing convolutional neural networks. So how many people have seen any work visualizing CNNs at all? A couple people? I know there's some, these are the papers that have really cool pictures in them, so they get a lot of hype. So we're going to look at some of those really cool pictures. So here we are looking at the features or the convolutions that are learned at layer 1. These are, given some input, these are the different activations that are coming out. It's just a selection of them. They kind of, I believe they just picked random things that are coming out. So yeah, fairly straightforward. But we can also jump this up to layer number 2, and we can see that at layer number 2, they're not just learning edges, but they're starting to learn a little bit more sort of geometric shapes for the given inputs. So these are now the activations at that convolution. So here around this one, you're starting to see curves. On this one, you're starting to see circles or points. You've got double lines here, a bunch of different ones. So if you're just you can plot these convolutions onto images and just get pretty pictures out. And this can kind of sometimes help you figure out what you're doing. Sometimes it does, sometimes it doesn't. It's mainly just cool pictures to look at least at this point. We can go up to layer 3. We can see that we're starting to get a little bit more on the geometric pattern side, combined shapes, stuff like that. Over here, we're starting to see activations around, heads and shoulders and stuff like that. Take this a little bit further, we can go to layer 4 and 5. Here we've got one, which is dog faces. It's actually learned, fairly high level features. Here we've got, it looks like the edges of glasses, or the edges of curved objects. Here we've got human faces at layer 5. Really sort of abstract edges along the edges of flowers. So this is the layers. This is the structure for the neural networks up at the top. So if you're ever working with a CNN, one of the cool things you can do is just visualize your activations at each layer. Just because everything's sort of still within the image space, kind of, you can just sort of plot it. Yeah.
So is this the same filter applied to all these images at layer 4, and then the same filter at layer 5 applied to those images?
Correct. Yeah. And so
there's more activations on the dog faces than the other objects. Is that what it's showing? Or?
No. It's showing that the same. So because it's sort of learning a hierarchical representation, so it's building from those from these sort of less abstract shapes. The same layer is able to activate differently for different inputs and sort of highlight different parts of it. Does that make sense? Yeah.
Saying that like in this in this picture, it's just taking the dog faces because the activation was highest.
Yeah. Okay. Yeah, so it's not that this one is it's not that this example of layer 4 is learning dog faces better than it's learning, the edges of circles. It's just that these are where the activations happen to be highest for this layer. So sometimes this can help debug. This is kind of hand wavy, and there's no real math behind a lot of these. There's math behind generating the visualizations, obviously, but what you do with them afterwards is kind of more art than science, and there's not really much. There aren't very many claims you can make about how to debug your network based on these kinds of visualizations. So you can think okay, I don't have. You can visualize all of your layers and see that for whatever reason your network's not picking up on some visual feature that you think is super important for your network. But getting your network to then pick up that feature is difficult. Yeah.
Also, for the picture on the left. Are this the picture for the input or the activation?
So on the right, right underneath layer 4, we have the image, and then on the far left, we have the activation at layer 4 for that image.
I thought before it was the layer that activated most when the image are like this, and they are the average of that input image.
I don't think so. Are you saying that from the paper? Or?
Yeah.
Oh, it might be. I believe I checked last night, and I believe it was just the activations of the layer. But I could be wrong. Yeah, I'm fairly certain it's just the activations coming out of that layer. All right. So we've got another interactive visualization for this guy. So this is Lynette. It'll take a second to load. How many of you guys have heard of Lynette? A couple people? Most of the people? All right, so the idea is that you want to, what's going on? The idea is that you want to, or this is LeCun's sort of visual classifier used for detecting images coming from MNIST. So this is the sort of first attempt at really doing character recognition while using convolutional neural networks. Assuming this thing loads, there'd be a nice visualization of it, but. Oh no, it'll be there.
Is there any visualization of neural network in NLP task?
Yes, we're going to talk about that in a second. Yeah. There we go. Yeah. So here we've got, we've got our network. We can visualize the connections between it. So, this is a fully connected layer. This is coming out of convolutions, or I think this might actually be a pool, but you get the idea. So we can draw a number, and we can see the activations coming through the network. And we can sort of see where different weights come into play. So, yeah. That's true. So sometimes it doesn't always work. It's fun to draw backwards 3s or upside down 7s and see what it thinks. But here, if we give it one that kind of looks like a 4 or looks like a 9, you can kind of see what's going on. So here's the input image down here on the bottom. Then we've got a first layer, pooling, second layer, and then so on and so forth up to 2 fully connected layers and then an output. So we're doing it across 10. So this example is using Lynette, but it's sort of agnostic to, this kind of approach is agnostic to whatever kind of network you want to throw at it, at least in terms of convolutions. Visualizing Rnns, which we're going to talk about later, is a little bit more tricky. So here we can see that it looks like this layer is good at detecting edges of things. This one's good at detecting, it looks like white space. Horizontal edges, vertical edges, curved edges, stuff like that. So we can kind of see that hierarchy build a little bit, not quite as well as with the other images, but this one's a little bit easier to visualize just because it's a small network and we can look at it easily. Yeah, so you can mess around with this. It's fun. But like I said, this is just a visualization technique that's kind of agnostic of implementation. So if you want to use it with Lynette, you can use it with Lynette, or if you want to use it with some other network that you're building on your own, you can do that too. So now visualizing Rnns. Unfortunately, this one's a little bit more difficult to think about just because there aren't pretty pictures we can look at, and if we're projecting activations onto some input, we kind of just have to do that in the text space as opposed to into the text space as opposed to in the image space, and so it's a little bit harder to interpret. So this is a great paper about visualizing. It's on the quiz, yeah. Oh, should I not cover this?
It's fine.
Okay. Okay, so this is just showing that, so the paper's on the quiz, but the paper's linked to it right here as well. But this is looking at the activations of specific neurons in the hidden state of an LSTM cell across your input. So you can see that, this neuron up here, tends to become more sensitive as it's expecting a new line character. And this one over here is activated almost exclusively when you're inside of a quotation versus something else. So this this was trained on data from the Linux kernel, just trying to do language modeling on code, and the other one was on War and Peace. So these more paragraph style ones and quotations are coming from War and Peace. And the ones that look like code are coming from the Linux kernel data. So here we've got one neuron that turns negative when you're inside of a curly bracket, and turns off once you're outside of a curly bracket. Here's one for detecting the starts and ends of I think it's comments. There's another one over here which is starts in a rather interior of comments as opposed to the starts and ends. Here's one that appears to turn off as you're getting closer and closer to writing a return statement as opposed to just writing regular code. And then, this one looks like it's predicting a new line. Oh, I'm sorry, this one at the bottom they claim is one that they don't think is easily interpretable, so I won't make any claims about that. But yeah, so there are ways to visualize RNNs. It's a little bit hard because you're not really projecting into visual space, which you can easily interpret like you are with images. But there are some ways of doing it. The other thing you can do is you can actually visualize the activations for the gates inside of the cells. So if you recall, there are some gates. There's a forget gate, input gate, and an output gate going on in the inside of an LSTM. So you can visualize their average states. So this is an example of, so they're using a 3-layered LSTM. The green dots are referring to the first layer. Blue dots are referring to the second layer, and the red dots are referring to the third layer. And the idea is that this is how saturated that gate is in particular. So if you recall, the gate is defining how much of a specific vector you want to allow in or out, or forget at each time step. So if the gate tends to be open, meaning right saturated, then you'll have a value way over here. If it tends to be closed most of the time, then you'll have a value way over here. So you can kind of see that at least on the forget gate, you are, at least for this network, you're tending to be either vary one way or the other about the way that your gates are opening or closing. Whereas in the output gate, it's kind of all over the place. The first layer is not really making any decisions about what to allow in or out to pass. It's just kind of just letting everything through. But as we started to get into higher layers, it starts to make decisions a little bit more. So you can kind of visualize what your network's doing. This is starting to get a little bit closer to being able to decide whether or not you're going to be, or rather, how to make design decisions based on these visualizations. It's still kind of hard to make claims about what your network's actually doing or how it's working, but you can start to make inferences if you start to notice bugs. So like if you have issues with long-term dependencies and you start to see that your forget gate is doing stupid things, then you can start to make claims about it. And maybe start to debug as well, but it's kind of hard. And you can do the same thing for GRUs. So we just did the example for LSTMs, but if you wanted to do the same plots for a GRU, there's nothing stopping you. These ones, look a little bit more, varied than the previous ones. At least it seems like they're, at least in layer 1, it's almost always more left saturated than it is right saturated. Just to be clear, these dots indicate how often, sort of like the ratio between how often it was left saturated versus right saturated. So if you run 100 examples and 0.5 of them are greater than, they define right saturation as the gate is greater than 0.9 or less than negative 0.9, or -1, or excuse me, or 0.9 and 0.1 depending on what type of gate you're using. So if it's right saturated, so meaning greater than 0.9 for 60% of the time, then you get a value of 0.6, and if it's right saturated for 1% of the time, then you get a value of 0.1. So that's how you find out those specific values. So it can be a little bit helpful for debugging, but it's kind of just a hand-wavy way to say, look, you can see what's going on inside when you kind of don't really know. Yeah. All right. So attention. we're going to talk about attention because it's super, it's super cool, but also you can like visualize it and then you can actually see where and why your network is making mistakes to an extent. Sometimes the results are hand wavy, sometimes they're actually, they actually help you. So attention is seems like kind of a daunting task, and I know we're going to cover it later in the lecture, so we're just going to do like the brief once over. Here are the general ideas to get you started. So the idea is that you've got this thing called an attention model, which is sitting in your network, and so here we've got a sequence-to-sequence model. So we're doing a sequence of inputs in, and we're generating a sequence of outputs, right? So the attention model is some sort of machine learning model. Traditionally, it's backpropagation, a model that can be trained via backpropagation, so you can train your attention model at the same time as you're training your network. This attention model is looking at two things. It's looking at your inputs, some input h, and the current state, the current previous state of your output. So it's basically saying for the first, let's say for H1, for the first input, and for my current state of generating outputs, I'm going to look at these two values and then generate some gate value that's going to define how much I want to care about this input. So you've got, it's not like some mathematical formalism. You've just got a neural network sitting in between saying that this is how much you want to care about this input versus this is how much you want to care about this other input. So we've only got one output that's being calculated for each input, which is basically just the how much you want to care about it. This is either typically a sigmoid or a tanh activation that's deciding that value. And then here's just the kind of formalism for it. So A is a learned neural network typically, or some backpropable kind of thing, and it takes in the previous cell state or the previous state, hidden state from your recurrent neural network, and the input that you care about, at least for this example. Those two get fed into the network, and then you get a number that defines how much you care about it. Then you do a softmax over all of those, and that gives you your A value. And then once you then you sum up all of those how much you want to attend to each input, and that gives you this new value C, which you pass into your decoder RNN value. So hopefully that makes sense. This is very hand wavy. I'm not going into like the motivation or the derivation. The only thing you need to care about is that these values that are coming out of the activation model, or excuse me, the attention model, is just a single value that we can visualize on a per input basis, right? So we can visualize these values. So if we're working in a domain that's like image classification or image, caption generation, excuse me. We can do two things. So there are two types of attention. This one is stepwise activation. This one is softmax activation. In between the two. So this one you're literally just saying this region I want to attend to, whereas this is kind of a softer distribution. So you can attend to multiple different regions. So this is given an image, and as you're generating this this phrase, a bird flying over the water, you can visualize how your network is attending to different parts of the image as you're going on. So in the hard attention, it's a little bit hard to visualize. It doesn't really seem to be making too much sense, but in the soft attention, you can kind of start to make claims. So some things don't really make sense. Like it's kind of hard to explain why there's an attention on the wings for the letter A or for the word A, or over, or of, or something like that. But at least in the case of a bird and flying, you've got two things that kind of make sense. It's focusing on the bird, and in terms of body and water, you're looking at sort of the region around the bird, and you're not focusing on the bird. So there's kind of a benefit there. The other thing is you can actually start to look at individual words and see if if the model's actually classifying things correctly. So here we've got a woman throwing a frisbee in a park, and we're looking at the attention values across the pixels for the term frisbee. And so you can see that it's kind of highlighted on mostly on the actual frisbee itself, but a tiny bit on the the people who are involved. Here we've got a dog, and it's highlighted on the dog, and this isn't. It's not always right, at least in terms of the underlying model. So this dog is not standing. But here we've got a stop sign, and it's focused very clearly on the stop sign, and we can kind of go through these steps for each one of these, but you can kind of see what's going on. Yeah.
Or like the more grammatical words, I believe that the word generation is basically just conditioning all the previous words, and then the hidden state is staying the same as before to like preserve information. So like for the words where the soft attention has less interpretation, it would just be preserving the attention back from before.
Is that the case? That's kind of cool, actually. Yeah, I didn't think about that. For people who didn't hear that, Jerry mentioned that if you notice, the soft attention map is preserving the meaning from the previous step almost entirely for words that are not identifiable in the image. So for an example like over, it's fairly close to the image for flying or something like that. So it's kind of preserving that meaning as we go on. And so we can also use this to diagnose errors a little bit. So here we have an image of 2 giraffes, it looks like, and it's claiming that it's a large bird standing in a forest, and we can see fairly clearly that this is not a bird, but it's focusing on the image of 2 giraffes. So we can start to make some claims that this is maybe an image recognition problem, or actually a problem with the it's not a problem with the decoder, it's more a problem with the encoder or something like that. Same thing with a woman holding a clock, or a guy wearing a hat and a hat on a skateboard. There are a bunch of different ones, but this is a great one over here. Man talking on his cell phone. It looks like sort of semantically he could be holding a cell phone, but it looks more like food to me, maybe a sandwich. I don't know, but you can kind of understand why these models are making the errors that they are, and hopefully you can start to use this kind of information to start to diagnose a little bit why your models are making the errors that they are, or why they're doing the crazy things that you expect them not to be doing. But yeah, it's just a starting point. A lot of times these can be misleading, or might get the right answer for the wrong reason, and so you may not want to change it. So yeah, but it can help point out errors. The other thing you can do is you can also do this with sequence-to-sequence models. So if you're doing an encoder decoder for sequence-to-sequence, you can map the attention across the inputs and the outputs. And the cool thing is that these look a lot like word alignments for if you're working in translation spaces. Sometimes you get an off by 1 error, sometimes you don't. It depends on what kind of model you're using. But you can do some pretty cool things with them, and at the very least, start to see if your model is, doing the translation wrong or learning the grammar incorrectly or anything like that. So if you know intuitively that the word order for this language that you're, in the machine translation example, if you know intuitively that the word order for your, target domain is different than the word order for your source domain, for your source language, and you see that the model is learning that sort of grammar incorrectly, then you can start to debug and or maybe generate features that are used to try and help the model out, get from point A to point B a little bit easier. But yeah, again, it's kind of hard to make some claims about what's actually going on under the hood, because we're only looking at a couple of test cases here as opposed to the entire data set or anything like that. But it's useful and they look pretty, so it's fun. So we talked about this a little bit earlier. So if we've got input data, or if we've got network data like hidden layers or something like that, inputs or outputs from hidden layers that are in very high dimensions, and we want to try and visualize it, how do we do that? So we can project the data in 2 different dimensions. So there are 2 kinds of techniques that are typically used for this. There are a bunch of others, but I'm only covering 2 for the time being. The first is called principal component analysis, which tries to take the data and to project it along its principal components, which basically means that it tries to reshape the data so that the first dimension or the first principal component is the most information dense component. So if you were to slide along that axis, you would cover as much of the data as possible. And then each component afterwards, the second principal component, the third principal component, would be respectively the next best axis for encoding that information. So this is a PCA of MNIST, I believe, and it's the common technique if you want to look at embeddings or you want to look at outputs from your network. But if you really want to visualize high-dimensional data in a way that looks well, or you want to do some clustering technique or something like that, then you can use TSNE, which stands for T-distributed stochastic neighbor embeddings, which kind of sounds crazy, but the idea is that it's a clustering algorithm. It's an unsupervised algorithm that is trained on KL divergence and attempts to bucket the data into into its group of nearest neighbors. And sometimes you can get pretty graphs like this. We're going to show some examples later about this. But for the most part, the thing you need to know is that the outputs from TSNE are typically stochastic, and so they won't be the same every time. So if you keep running it and you get different answers, it's because TSNE is like that. Whereas PCA should theoretically be deterministic. You're getting the same principal components for every input data as opposed to, irrespective of ordering or something like that, just because you're analyzing the principal components. So that's why when you're visualizing embedding spaces, you want to use something like PCA. Whereas if you're using TSNE, or you want to visualize just high-dimensional data and you want to see kind of what it looks like, you can start using TSNE. These aren't restricted to 2 dimensions. I'm just visualizing 2 dimensions here. There are a lot of times where you can visualize up to 3 dimensions or down to 1 dimension or whatever you want. The other thing you can do is you can also combine the two. So you can take an output of TSNE and then plug it into PCA, or PCA into TSNE, and try and get better visualizations if you want. There's nothing really stopping you. It's kind of however you want to play it. So there's this great demo of this data, of these systems, which kind of goes into the detail a little bit, but we'll just look at the TSNE visualization. So actually, here's PCA. Oh, no, here's PCA. We'll get there. All right, so here's PCA. It's kind of hard to view it. That's a bad example. Oh, man. All right, we're going to try with TSNE. So here we've got all of our data, and this is completely unsupervised. The labels that we're getting are sort of applied after the fact, but it's able to just bucket the data based on its nearest neighbors. So the idea is that it's taking taking an example, looking at the couple nearest neighbors for it, the T nearest neighbors for it, and then trying to sort of associate those within the space as best as you can. So it's an iterative solution. It gets there in time, but it's not perfect. Yeah.
So this is on the input data. So like if it's a 28 by 28, it's looking at 784 dimensions, and then just
yep. Yeah. So this is what the we're going to show the IPython notebook in a little bit, but this is just going from 700 and I think it's 84 dimensions down to 2. So it does a decentish job. There's some examples further at the bottom which are not loading that do it in 3 dimensions. So this is super cool if you guys want to look at it. The visualizations are great. But here we can look at some data, some examples for this in code. So this is using sklearn, which is slightly different from PyTorch. This is more of the traditional machine learning techniques, things like SVMs and TSNE and PCA. So the idea that we're going to go through is just we're going to try and visualize pure MNIST data using PCA and TSNE. So here we're going to use this wonderful function that just gets us our MNIST data. And this is going to get dumped out as a 70,000 cross 784 matrix of our training examples. We're going to train our or get our labels, and then we're going to get our targets. The targets are going to be integers between 0 and 9, which represent the labels for the MNIST data. We're going to shuffle the order, just so that things stay a little bit different every once in a while. Print out some info for debug, and then we're going to generate some colors so that when we want to visualize them later, we can actually do that. So right now we just have 70,000 examples of 784 dimension each. So obviously very high dimensional data. This is just pure pixel values. Yeah. So sklearn makes it super easy to do PCA on this kind of data. So you literally just do PCA, you define your number of components. So here we're going to be asking for the top 2 components. You could ask for the top n components and then only select the top 2. It's up to you. The result's not going to be any different. And then the PCA result that we're getting out here is a projection of this data. So this new matrix coming out of PCA result would just be 70,000 cross 2, because we're asking for the 2 principal components. And then we plot it, and we get a data point or set points of data like this. So it's kind of done a little bit of separation for us. We've got it looks like our 1s being centered right around 0 and at the bottom. We've also got our 7s, it looks like, being shifted far to the right, 3 being shifted all the way to the, or excuse me, our 7s being shifted all the way to the left, and the 1s and the 2s being shifted all the way to the right. So it kind of helps. We can start to see how our data is looking a little bit, but it doesn't really do very much to actually help us and tell us what's going on right here. So we can kind of see that the 1s themselves are a little bit more. They're all a little bit more self-similar than the 9s, which seem to be spread out all over the axes, whereas the 1s are pretty dense. So you can start to make some claims, but it's not really doing too much for us. But if we really want to try and visualize this data, we can start using TSNE, which is the technique that we were talking about before. Like I said, it's just doing the KL divergence of a projection between between 2 or T neighbors. There's a little bit more math to it, but you guys can look at the paper for that. For these purposes, you just can think about this as being a learned projection. So you downsample. We're going to downsample the number of examples just because this is a training. This needs to be trained. It's going to take a while, and we've only got a couple. We don't have all day here in class. So we downsample it, and then we just drop it into TSNE. We ask for 2 components, and then we define some perplexity values and a epoch limit to actually do everything. So it's been run already, and then we plot everything, and then we get this plot, which I think is a decent representation of the data. Remember, this is completely unsupervised, so it's literally just taking the data and chunking it out into its respective buckets. So every time you run this, you'll get a different result, but now you can start to make a little bit more claims about what's actually going on. So you can see that it looks like 9 and 4s are pretty interwoven. So there's kind of a subtle difference between the 2 of them, but TSNE is having a little bit of trouble figuring it out. And so that kind of makes sense intuitively because the shape of the number 9 and the shape of the number 4 are fairly similar to each other. And you can talk about how it looks like 1s are fairly spread out across the distribution, while things like 0s are fairly compact. The representations all seem to be fairly close to each other. So now you're starting to actually be able to make claims about the shape of your data, what things look like, what things are similar, and what things aren't. So this is helpful for obvious reasons. Because this is trainable by backprop, you can sort of do this as much as you want for as long as you want. Sometimes the projections are very good depending on your initial conditions. Sometimes they're awful. Sometimes you don't really know what you're going to get on the other side. Like I said, you can do. We haven't done this here, but you can do PCA into TSNE. So if you wanted to, in fact, we can do that right now. So static code block. And so we've got our values coming out of TSNE, and we've got our values coming out of PCA. So we'll give this a run real quick. So we're going to ask for, let's say, the first 5 principal components coming out of PCA. And PCA runs super quick. Oop, I missed train. Oh, I need to run the whole.
Do you like the collab notebooks?
I do like them. It's nice. You know, you don't have to worry about things, you know, not having libraries on different computers and stuff like that. It's fun. Although we'll see why this isn't running. There we go. So here we're going to ask for the first 5 principal components. That's going to chug for a second. And that's done. And so then our variable name was PCA result. And so then we can dump PCA result into TSNE. So now we're going to be taking the first 2 dimensions are going to be exactly the same as this image, but we're going to get 3 additional dimensions that are somewhat representative of our data. Then we're going to dump this into our TSNE. So this is going to be a 5 cross 70,000. Actually, let me do this differently. And we're not going to have labels, unfortunately, because we're going to be... Actually, is the order? Yeah, the order is going to be maintained. That'll work. So yeah, let's give that a run. This should chug for a little bit. There we go. And then once it pops out, we can go ahead and plot this. So yeah, TSNE is typically a lot slower than PCA. So here we were only giving it 7,000 examples with dimensionality of 5, whereas before we were giving it, for PCA we were giving it 70,000 examples with dimension 784, and PCA finished within a few seconds, whereas this one is still chugging. So it'll take a second, and then once it is, we'll press run here and see what it looks like.
So would you do this more in sort of a exploratory analysis of the data before you start building your network, or is it after the network is built? How do you tend to?
So there are a number of different ways you can use it. So you can do it as an exploratory method, and you can just say like, hey, it looks like this class of example is, for whatever reason, super spread out, or is very similar to this other example, and so maybe we need to think about constructing features or building some, model that intuitively takes care of those, some aspects of that data that we think is going to be important. Or you can do it for visualizing your network itself. So there's the visualization. So you're getting a different result, not quite as good as the other one, just because. You stripped away a lot of the info and tried to, you projected the data. You projected the data already into here, and if you look at this data, it's obviously not as, probably not as separable as just the raw data. So you've lost a lot of information. So some of it's still there. You're able to see that the ones, like we saw up here, these ones were pretty visually separated, and so TSNE was able to spread those out a little bit more. Same with the 6s, which were up here a tiny bit. But yeah, sorry. So to continue off your question. You can do this as an exploratory technique to try and figure out, what your data looks like, or you can do it on your. You can't really do it with TSNE, but you can use PCA to visualize the outputs of your hidden layers and see, how your hidden layers are sort of generating or projecting your data. So you are going to lose a little bit of information there because it's a projection of a projection. So you're not really going to be visualizing your input. You're more going to be visualizing what your network's actually doing. It's not as informative. It doesn't really transform easily as training happens. I wish there was a way that you could visualize the network as it's training and you could see how the shifts are happening. But at least for high dimensional data, that's really hard to do. So yeah. So then jumping back to this. We're getting close to this stuff. All right, so visualizations. I've kind of been saying this as the lecture has gone on. We don't really get anything out of them. We're starting to get things out with attention and a little bit out with PCA and TSNE. But the problem is that at the end of the day, these are mainly just cool images to look at, and it's kind of hard to diagnose what's actually going on inside your network. You can start to make claims. You can see kind of what the network is doing, but in terms of using these visualizations to inform design decisions about your network, or trying to fix errors based on the things that you see, it's still super hard. So if you're in a specific case, where you see your attention doing something, and you can actually diagnose it as an encoder problem or a decoder problem or an issue with your embeddings or something like that, that's great. But a lot of the times it's kind of just hand wavy. This helps because we can look at it. But yeah, maybe in due time it'll figure itself out. People will figure it out. But for now, it's kind of right where it is. So then with that, we can start talking about the Docker stuff. And well, first I'll ask if anybody has any questions, and then we can jump into the other stuff.
So the Docker stuff is important because it's going to affect your next homework.
Yes.
So please pay attention.
Ben, do you want to do it on this computer, or I don't know if you can or not.
Yeah, I guess you can actually. The downside is, so apparently SourceForge and GitHub both went under these like random DDoS attacks.
I saw that, yeah.
Which apparently also just took down the Sphinx download. This is all messed up now, so that means the automated build is not currently working, and I gotta fix that.
Okay.
But that means Sphinx went down, so we'll have to do that part for you.
Okay.
But
the mic's in the computer.
Sorry?
The mic is in the computer this time.
Oh, the mic is in the computer.
Oh, both of them are working. Okay.
That is good news. Okay. So has anyone heard of Docker before? Has anyone used Docker before? Haven't seen it? No. Okay. A little bit here or there. Okay. So what? Oh, great. So we're gonna run through this really quickly. So we have the tutorial. Where's our deep learning tutorials? Yes. So the tutorial repo you guys have probably seen before, and that's where we've been putting a lot of our recitations and stuff. But we also have these other repositories that you might have wondered what they're for. These other repositories are Docker. Well, they're GitHub repositories, but they store Docker files. What a Docker file does, for example, this is the machine learning GPU Docker file that we have. The other ones, there's one that's exactly what we have on Autolab, which is important to know. And there's another one that's like just a base image. So what a Docker file actually is it looks like a set of install instructions. So when you guys are running into, as a side note to Docker, Docker will create these virtual images and install them themselves, but you can feel free to look at these as reference. But so basically what Docker does is you create a virtual machine image, you script out all of the installs and configurations in this Docker file that looks like this, and when you run the Docker image, it ends up creating a Docker file. These Docker images are most commonly stored on Docker Hub. So Docker Hub is a service that's kind of similar to things like GitHub and et cetera. It's a cloud-based service. I think that was the name. Yeah, so this is a cloud-based service that stores repositories and actually runs the builds. So we have that Docker file script, that entire script for installing PyTorch and Sphinx and CTC loss and all that stuff gets automatically run up on Docker Hub. So they actually are nice enough to run it for us and host the images. So that means you can see the images that we have, and you can go through and see, when they were installed, whatever. But the command that you end up using is this Docker pull. So, so do you know I can display the other computer. I guess probably not.
Not
Maybe,
easily.
but I can. Okay. Probably just show some videos or show some like Docker cheat sheet or something to show you what it actually looks like. But what I think I'll do is maybe make like a YouTube video or something and post it for the actual interactions. But what you can do with Docker is that you only have to worry about installing Docker on your Amazon image or on your local computer or wherever you are. And then you pull our VM, and if you use that VM to run things and everyone has the same VM, you pre-build it, you have a new Amazon image, all you do is create a new image, apt install Docker or Docker pull, and then run something. This also might come in handy in terms of your projects, depending on what you guys are working on. That means your group what you can do is you can like fork our repository or make your own, whatever you want to do, but you can install all the special software and weird little things that you want for your group to have, and that means everyone who's running, everyone who's a part of the group can just add something to the image, everyone has it. It's a really nice way to share and make sure everyone's on the same page in terms of things. So if I can't really pull up the Cygwins and stuff, so I'll post the video with Cygwin and how it interacts. That means you can use Docker for, you can go all the way as far as run PyCharm in your Docker on Amazon, and then just have a full-featured IDE on your computer that you're working on your laptop that is piping straight through to a VM out on the cloud. So there are all kinds of really fun configurations you can do. You can use Docker to run Jupyter and use that to interact. You can use Docker for just headless, mindless processes because it's so easy to run. You can write a script very easily that creates an Amazon image, downloads the Docker file, and then runs your code. So when you're doing something like that, that actually enables you to start off like several instances and or organize your stuff that way. So if you do start researching through Docker and Google through Docker, you will see kind of what they're talking about. But it's that there's any tool chain. You can also run Docker on Windows. You can also run Docker. I mean, here's several different installation methods. That means if you are like, oh no, how do I run PyTorch and CTC decoder and get all of that stuff installed on my Mac? Yes, you can get it working on your Mac, but another option is get Docker running. You're running a pure Ubuntu environment with everything exactly the same as everyone else has. So in terms of weird segfault issues you guys are posting or whatever, like, we're happy to help with installation problems, but one workaround is as long as you have Docker running, everything else installation-wise we can kind of take care of as a group. And actually with that in mind, I will say that is a public repository I was showing you here. So if you want to fork it and make something different, go for it. If you think like, oh, we forgot to add pandas, so, I mean, we have pandas, but some random library that SciPy, scikit-learn, whatever, we forgot that, then you can basically fork this repository, you add one line, you push that to our repository, we hit accept the pull request, that will automatically go out to Docker Hub, and then everyone in the class now gets to have whatever it is on their computer. So this will be hopefully a nice direction for organizing things. And as I said, in terms of installation, the main things which we've added in the last couple of weeks to this Docker file, and this has been up for months now, but the recent additions are installing Pocket Sphinx and installing the CTC encoder and the decoder, which we kind of briefly mentioned in the last recitation, but it's important to mention that CTC is not a part of PyTorch. So there's a Baidu produces a CTC version, and then someone named Sean Naren has a port of that into PyTorch. So that's what we can use for the loss. And then there's a separate decoder, which is actually, we found out was based on some of Bix's code. But that's the decoder. So both of those need to be installed, and we have Jupyter set up, things like that for you right here. In terms of running Docker, it's an entirely separate environment. So you say Docker run the name of the environment in this case, which in our case would be CMU deep learning, the full name of the image, which we will give you. And don't worry about it, we will post plenty of commands to help you guys out. But
so we need to use Docker to install which kind of package?
Yeah, so you don't need to use Docker to install. I'm sorry. Docker is a virtual machine,
Yeah.
so it means it has packages on it.
Yeah.
You never need to use Docker, but using Docker means we can have a virtual machine that has everything pre-installed, and then in order to use Docker, you just need to install Docker.
Yeah. It seems in the Amazon server we have already have all kinds of package, deep learning package. Right?
Yeah, you may or you may not, but also it's that this is for your own Dockers.
Just
If you look,
option.
yeah, it's an option, but also if you look through, like this is Docker Hub, like there is an official PyTorch Docker Hub, you know? Like PyTorch, as part of their development toolchain, puts out their official like machine learning VM from pytorch.org that is the PyTorch, you know. So you can always install PyTorch on your own, but it's just nice to have that as an option. And like I said, it's also nice for kind of syncing things up between people. So like you might have a different TensorFlow than everyone else does, but like I can put out, here's our auto-grading image, that is exactly the code that you're going to be tested against. Or, you know, you're working with a group of 4 people and you all have a different version of TensorFlow. It's like here, we've all got exactly the same libraries. We've all got the weird configuration set up. We've got the paths like the same. So it hopefully can avoid some of the weird issues. And also for the sake of like spawning off new instances really easily, that will really help you. So depending on how much you need to, you know, parallelly just dump out a bunch of VMs and you know, run a bunch of parallel processes. So
someone makes a pull request and you accept it and update the Docker image, and I'm using Docker. Do I have to manually update my?
Right, you would have to run the Docker pull command. So in terms of actually using Docker, I guess any questions about like what Docker is or you might want to use it? Anything along those lines? Okay. The main Docker commands you're going to be using, and again, I apologize, we don't have a putty session set up or something like that right now, but it'll be posting that. Docker pull will pull an image. If the image is there already, it will check to see if you have it already, and if it's the same version, then it won't do anything. So there's no real harm in calling Docker pull just in case to check to see if there's something new. You can think of that as like your git update equivalent. And then Docker run is probably the main thing you're going to do. And run takes in 2 parameters, which are the name of the image, which would be, you know, PyTorch/PyTorch, or CMU Deep Learning 11785 / machine learning GPU. So they can get very kind of long, and then the command you want to run. So if you just type bash, then that means you end up in a bash shell of a virtual machine that's going to be the same as everyone else and has things pre-installed. Or you could, that's if you want to do something interactive, but you could also just directly run Jupyter Notebook or PyCharm, or you could run Python, and that's probably what you'd be doing for your headless processes.
How does storage work in Docker? So is any files we create within the Docker, the container is stored in the container or on the local machine? Or?
Right, so containers are temporary storage. Let me go down to mounting. So in terms of like main things you need to know, that's a very important point, which is, I hope they actually have volumes. Here we go. Right, so they all have their own kind of temporary storage, and that's the other nice thing about Docker is you're not going to mess the image up. It's spawned off a clean, fresh instance each time you want to run it. You can restart it. You can start 5 of the same Dockers if you want. So then the question is, how do you store what you need to store? And it's this -v option, which is mounting a volume. So basically what you'll do, and the shortcut that I'll do a lot of is, everyone knows PWD is Linux for the present working directory. And if you put something in backticks, that means to run it and then use it as part of your command. So if you do something like, I don't have a great place to type here, but if you say docker run -v backtick, PWD backtick, colon, and then where you want it is like, host or, mount data, whatever. So that would be like, take my current directory where I am right now, and then in my virtual machine, I'm going to see it as mount data. So you would do something like docker run, do your mount, and then you would want to do CMU deep learning 11785 / depending on which image, and this might be your image, it might be something else, and then you can drop into the bash prompt, or you could try running Python, and if I wanted to run one of your Python code, I'd be running the code in /mount data myscript.py, whatever it happens to be. So what that means is these commands do tend to get very long, and that's something you kind of get used to. So there's definitely a learning curve to being able to use Docker, but I do think it's a useful skill. And even if you don't, well, definitely come to us if you have any issues and questions with this, but at the bare minimum, what we think you can do is if you're trying to install things yourself, then it should be very obvious from reading this kind of script. Like if you want to install it yourself, run wget and try to get that image. Like if you were doing it piecemeal or on your own computer, wanted to modify it, this should give you a general structure for all of everything that you're going to need to install and use. So in terms of if you're using PyTorch for homework 3, and I don't know if anyone's ever read homework 3, everyone's still on homework 2, but those are the 3 things you're going to need are going to be Sphinx, CTC decode, and warp CTC for the loss. All right.
You mentioned Sphinx is down now?
Yeah. It's SourceForge right now. Like all of their boost is down, Sphinx is down. Like everything's kind of rearranged. I don't know who's doing it. Someone and it's like who would attack SourceForge, and who would attack GitHub? There's like a massive botnet, or it actually wasn't even botnets, but yeah, there are massive attacks on GitHub and SourceForge this week, and I can't imagine any hacker doing it, and I don't know what weird foreign government could be planning something for that, but that's, it's weird to see stuff like that being the target of an attack, personally. Okay, so any questions on that stuff, or we can take some homework questions. We still have a few minutes left, which I hope we do.
Yeah, we got 10 minutes.
Oh, great, all right, yeah. Yeah, so like I said, I'll post all the commands, and as you can see from the command I started to type, these commands will get very long, but once you kind of break them down piecemeal and understand what they do, it means kind of 1 or 2 commands to get any machine up and running with everything together. And even if you don't, here's how to install. Okay. So anyways, how is everyone doing on... Sorry, you had a question?
I was just going to ask, do you use PyCharm? Is that kind of your main idea?
Oh, yeah. And that was actually why I wanted to have this up and running in the computer, but I'll just try to post some videos. 2 important things that I've been talking to a lot of people about are, just use an IDE. It doesn't make you, more manly or whatever just to use, Sublime or something, but it's you've got something built in, you run your code crashes, you click on it, you're going to the line where it crashed, and then you right-click on something and you see the function that called it, and you click on something else and you go to the docs, and everything's so much easier. Especially when you're starting out, and especially when you're trying a lot of different things, you're not going to remember the name of every single parameter, and just having something with nice autocomplete built in will save you a bunch of time. It's, you start typing the parameter, you hit tab, and then you're done with the line, and you're not constantly going back and forth with documentation and stuff. So, it doesn't have to be PyCharm. I don't know if you have any, or if anyone else has, a shout-out suggestions. Eclipse is pretty popular, or whatever, but
it's Spider, which is in Anaconda.
Yeah, I haven't played with it a lot, but if you feel like it makes you significantly more productive than you would be in Notepad, then that's a good thing. So that's one thing to keep in mind. So I just happen to put it on here so you guys can use it. And like I said, you can forward everything. If you guys are not IT experts, definitely ask us. But you can run things like different IDEs in your AWS or wherever and just forward things back and forth, kind of like we were doing earlier with Jupyter. So that was one part of the question. The other part of the question was, actually the thing I started to talk about was, I really recommend that, especially after this visualization lecture, that you take to heart, getting visualizations. That I feel like many people have been focused on just getting their code to work, which is, a valid point. You guys are learning PyTorch, and it's just I got it to compile, hooray. But really what you need to be doing is getting constant feedback so you can make informed decisions, which is why I've been pushing things like the like the TensorBoard and different visualizations with it. And keep in mind, TensorBoard does work with Inferno, and I know some people were having weird installation issues, but here's something where it's installed and it works. So yeah, just having something where like every 30 seconds you've got an update of what's my current loss, what's my current accuracy, and then like once a minute I've got what's my current validation. You can go do whatever, but you've got that web page up, you're constantly monitoring it, you can make those decisions. You're not like running it for hours and then coming back and being like, oh, it never did anything. Like you want a curve and you want to see like, oh, the curve has an elbow, so maybe it's a good time to stop and try something else. And I'll also try to post our kind of TensorBoard graphs. I don't know if you guys have noticed those on Piazza yet, but if you're running something like TensorBoard to see your loss all the time, you can look at ours, and if it's like, because our baselines are just random numbers, to be honest. It's like, they are very much like, based on our experience and stuff, but like these are zero tuned to anythings. So like, if you're getting something significantly worse than that, then it's likely like a coding or something else that's like way off, as opposed to, maybe I should just run it for a couple more hours. And most of our examples are like 10 to 15 minutes of GPU time. So like if you're running, you run your TensorBoard, you run it for a few minutes, you look at what the graphs start to look down, and like 2-3 minutes later you can tell if it's on the right track or not, and not waste your time.
You're generally running on P2X large?
Yeah, I think that's what we've largely been recommending. Yeah. Okay. Oh, sorry, was there questions back there? Stretching? Okay. Okay, cool. So any specific homework 2 part 1 questions, just to get out of the way? Everyone's good on that? Okay, homework 2 part 2. Where are you guys on that? Is everyone done? Is everyone submitted? No hands? Very shy.
I spent 5 hours trying to get TensorBoard to work with PyTorch and Inferno.
Okay. Well, I'm glad we had this discussion today. But yeah.
I would suggest even maybe like having this as recitation number 1 would be great.
Yeah, it was funny. We brought it up in recitation 1, and it's like 3 slides in there, I think, or maybe it was recitation 2. No, it was 1. Yeah, I think we had like a slide, but it's the kind of thing that like you don't realize how valuable it is until you have like, and this is just, we've got a couple of frameworks here, but especially if you're doing like a lot of linguistics and NLP type stuff, it's like you're going to have like NL Toolkit, and you're going to have some HMM software, and you're going to have all these weird like, because especially a lot of this stuff that got like really popular and like that stuff, it's like they're all C libraries with yada yada on them. Like, if you guys are here for the machine learning and language side of things, you might not know a lot about the compiling side of things. I don't know. But some of the builds do get to be a pain. Yeah, but actually that is good to know. Maybe fit is like a recitation 1 or 2 or something.
We can hype that up a little more.
Yeah, just like yeah, and the other big thing that I really wish we made a big point of is like, here's how to get the graphs, get everyone sold on the graphs, because it's really the hyperparameter tuning that's the hardest part of the class. Once you get past the can I compile and does it actually run? Yeah. So highly recommending both of those. Okay. If anyone has questions, I guess we can stick around, and we've got office hours in a little bit. So, all right, good luck, guys.
Where are the office hours at? The new sign on?
I think so, yeah. Unless we're going to do a corral.
Apparently we're supposed to reserve those. I don't know. Yeah.